Welcome back, everyone. In this video, I want to look at comparing the energy required to heat a substance versus the substance undergoing a phase change. And a typical example of that is when the effect of cooling on a body when you drink some water, 100 milliliter of water, versus when you, for example, sweat. And then, of course, sweating is the evaporation of water, whereas drinking is just you heating the water in your body and your body heat being absorbed by that water. So, the example here specifically says an athlete has just finished running a marathon. Compare the cooling effect on the body when 100 milliliter of water evaporates during perspiration as sweating versus drinking 100 milliliter cold water at 5 degrees Celsius. And the water is assumed to heat up to 37.5 degrees Celsius. And then we're given the constant values that we would require. Now, I've actually already did this question, but I forgot to turn on my mic. So I'm just going to talk through it because, there's no use in me just rewriting the thing again. So in the first case, we look at water evaporation. So to calculate the heat of vaporization, we look at the enthalpy of vaporization and we multiply that with the mass, because if we look at the heat of vaporization, which is called the enthalpy of vaporization, you see the unit is joule per gram. In other words, if we take the mass of the substance and we multiply it by that heat of vaporization, we know how much heat would need to be applied to that mass of substance to get it from the liquid phase to the gas phase. So in other words, we know that we would need to give at least 226 kilojoule to the water, to 100 milliliter of water, for all of it to evaporate. But listen to the words carefully. I need to give that amount of heat to the water. That means my body, or the athlete's body, needs to give off that amount of heat. In other words, the heat that the body gives off is the negative of that. So the body loses that amount of heat. Right, so in thermodynamics, the negative indicates the loss of heat. So meaning the body loses 226 kilojoule. Okay, so that's the first one. The second one is heating. So in the second case, we heat 100 milliliter of water, which is 100 gram, from 5 degrees Celsius to 37.5 degrees Celsius. And we use the specific heat capacity to determine how much energy does it require to heat so much water from 5 degrees to 37.5 degrees Celsius. So let me just get that in for you on one page. So you use heating is equal to mCs delta T, and you will calculate that the water needs to absorb 13.6 kilojoule of energy to heat by, 32.5 degrees Celsius. That means the body needs to expend 13.6 kilojoules. In other words, the heat of the body is minus 13.6 because it releases 13.6 kilojoules. Therefore, the perspiration, of course, has a much greater cooling effect than the drinking of water because it creates a greater loss in heat. You can see it's a much greater loss. It's by almost a factor of 20, 18 maybe, greater than what drinking water is. That's why your body sweats and you don't just drink water. So this is, of course, a very summative thing, but it's in general why your body sweats and why sweating is actually a very good mechanism for your body to cool you. But that's the idea here. It's how to remind yourself of how to think about evaporation versus heating. Heating a substance, it remains in the same phase, so we use its mass and its specific heat capacity. Whereas with a phase change, we just use its mass and its enthalpy of vaporization, or its heat of vaporization, so to speak. Right. So that's the idea of this question, and it gives us an idea of just quickly comparing it. And of course, you need to remember whatever happens to the water, the body needed to have the opposite happening to it. So if the water absorbed that heat, the body needed to give off that heat. All right. Thank you for watching. I hope this was informative and useful as always. And I'll see you in the next video. All right.